Today we're going to talk about drawing a phase portrait for linear systems that have real eigenvalues. So last class, we talked about finding the straight line solutions, and so we can draw those in the phase plane. And we can use those two straight line solutions to write a general solution. But today we're going to be focusing mostly on drawing the qualitative phase portrait. So to learn about how to draw the phase portrait, we're going to practice what we learned last class and then draw some conclusions based on the examples that we see. So I'm going to have you in your groups. I've told you, I've written out exactly how to do it. You don't have to remember. Each step it says find the eigenvalues by solving this equation, right? So I want you to work your way through number 1 and then we'll talk about the results. Okay, everybody seems pretty good with finding the eigenvalues. I'm just going to review how to get the eigenvectors from them. Okay. So eigenvalues, we take the determinant of a minus lambda I. So a minus lambda I ends up looking like a is 8, negative 11, 6, negative 9, minus lambda times the identity matrix, which is 1, 0, 0, 1. And we get 8 minus lambda, negative 11, 6, negative 9 minus lambda. So now I want to find the determinant of that matrix and set it equal to 0. So the determinant, that's AD minus BC, so 8 minus lambda times negative 9 minus lambda minus negative 11 times 6. Set that to 0. And this turns into a easily factorable quadratic, and we get lambda 1 will be negative 3, and lambda 2 is 2. Okay. All right, so we have my two eigenvalues. I have to find the eigenvector associated with each one. So eigenvectors are vectors that when you plug them in, right, this is the direction in the direction field. A times a vector gives you the direction. Has to be a multiple of the vector itself. So we're looking for the eigenvectors. Those are the vectors that lie on the straight line solutions. So we set A times some unknown vector that we're looking for. So let's use lambda 1 equals negative 3. Finding the associated eigenvector, we set A, which is 8, negative 11, 6, negative 9, times some unknown vector, we'll call it x1, y1. Put the 1 subscripts to remind me that this corresponds to lambda 1. Has to equal lambda, negative 3, times x1, y1. That's the definition of an eigenvector. What we're looking for is that when we plug the vector into the differential equation to get a direction in the direction field, it is a multiple of itself. Points in the same direction as itself. So now this is a system of equations I need to solve. So I have 8x1 minus 11y1 equals negative 3x1. Just doing the matrix multiplication. And then I have 6x1 minus 9y1 equals negative 3y1. Sorry, this should say eigenvalue. Well, yeah, yesterday we just, the only difference is that we solved the equation AV minus lambda V equals 0. So that's the only different thing that we were doing yesterday. So I'm looking for x1, y1 vectors that solves this system of equations. This doesn't seem right. 11x1 minus 11y1 equals 0. And this one says 6x1 negative 9 plus 3 is negative 6y1 equals 0. These two equations are multiples of each other. Right? So that means I don't have one single solution, right? Usually we say two equations, two unknowns, you can solve it, you have a single solution. But when the two equations are multiples of each other, you have infinite solutions. And all the solutions here lie on the line y1 equals x1. When x and y are equal, then you get that it solves both equations. This is my eigenvector. Well, all my eigenvectors lie on this line. So for example, 1, 1 would be an eigenvector associated with lambda 1 equals negative 3. All right, you find the one associated with lambda 2 equals 2. You can speed up some of the arithmetic by just telling me what you got. When we solve this equation, a times v, 2, right, because we're now using lambda 2 equals 2. And solving the equation ay equals lambda y. Okay. So what do you get for, let's just do it out. So we have 8x2 minus 11y2 equals 2x2. And 6x2 minus 9y2 equals 2y2. Oops. Okay, so simplify these and I get 6x2 minus 11y2 equals 0. And this one also comes out to 6x2 minus 11y2 equals 0. So I really only have one equation. One linear equation in x and y. That is my straight line solution. Every vector along this line is an eigenvector. So I solve this, I get y2 equals 6/11 x2. That's a straight line solution. Some vector on this equation might be 11, 6, right? If I plug in 11 for x, y would have to be 6. So this is one particular eigenvector. Out of an infinite number. Okay, all the vectors that lie on that line. All right, so now we're going to use each eigenvalue and associated eigenvector to write two solutions. So I've got y1 is e to the lambda 1, which is negative 3t, times the vector that we found that was associated with the lambda 1 equals negative 3. Any vector. One of them would be 1, 1, because my straight line solutions were y equals x. And then my other equation, my other solution will be y2 is equal to e to the 2t, because this time lambda is 2. And one of the vectors, one of the eigenvectors we found associated with lambda equals 2 was 11, 6. Or 1, 11, 6. 1, 6, 11s, whatever. So we've got two solutions. If they're linearly independent, I can take a linear combination of the two to get a general solution. So to make sure they're linearly independent, you just plug in 0 and make sure the resulting vectors are not multiples of each other. You can, because they're always going to come out to that, yeah. So I'm just trying to drive the point home that, remember, you can only do this thing where you combine them in a linear combination if the vectors are linearly independent. So I was just reminding you of that. But in general, when you have two distinct eigenvalues, they'll always be linearly independent because they're on different straight line solutions. Okay, so I can combine them into one general solution, k1 times y1, which is e to the negative 3t times 1, 1, plus k2 times y2, which is e to the 2t times 11, 6. And you can multiply it out or not, as you prefer. All right, so next, we want to sketch the two straight line solutions, which we found equations for. The one associated with lambda equals negative 3 was the line y equals x. So if I graph the line y equals x on here, because this is just the xy plane, shouldn't put an arrow on it. So this is the line y equals x, one of my straight line solutions. And you can see that the vectors are all pointing, or all tangent to that straight line solution. And we can tell from the vectors that the solution goes like this, heads towards the origin. We also know that why? Because the lambda was negative. We found this line from y because lambda 1 was negative 3. When the lambda is negative, the solutions go towards the origin. When it's positive, they go away. Okay, so my other straight line solution, the one associated with lambda equals 2, was y equals 6/11 x. So I go over 11, up 6, like about over 11, up 6, about right there. Is that right? And I graph this line. Not very straight, sorry. There's another straight line solution. And I know that that one was associated with lambda equals 2, which means the solutions are moving away from the origin, which is supported by the vector field. So now I want to sketch in several other solutions just following the vector field, and that'll create a phase portrait. So anything over here kind of looks like, goes like that. That's not very, there we go, like that. And the arrows are like that. And in between my straight lines, I have U's kind of like this. And you can put the direction on using the vector field. And follow these. Oops, too much curve. Mm-hmm. Correct. Yes, they're all just not very curved. Yeah. Yeah, that's a good observation. So this is my phase portrait. I now know the quality of all the different kinds of solutions I can get. 2 straight line solutions and 4 other kinds of solutions that can happen. And it turns out that this is not unique. This happens every time you have 2 eigenvalues where one is positive and one is negative. So we call the origin here, my fixed point at the origin, is called a saddle. It kind of is supposed to remind you of the shape of a horse saddle. So like if you put a drop of water right in the middle, it will just stay there. But then if you put it, slightly away from the origin, it's going to slide off in a direction dependent on where you put it, right? Yes, if it's on the straight line solution, it could go back to the origin. Yes. Yep. So this phase portrait is typical whenever you have one negative and one positive eigenvalue. When the solutions around the equilibrium point behave like this, we call it a saddle. So that's one kind of classification for the fixed point 0, 0. You could have a saddle. All right, so to find the particular solution that satisfies an initial condition, we set the general solution, y of t, which was k1 e to the negative 3t 1 plus k2 e to the 2t 11/6. We plug in 0 for t, and that's going to give me k1 times 1 plus k2 times 11/6, which has to equal my initial condition 0, -5. And then I saw this is just a system of equations. This says k1 plus 11 k2 equals 0, and k1 plus 6 k2 equals -5. And what do we get? 2 is 1. So then you just plug those into the general, and you've got your particular solution. All right, so 2 and 3 are a little bit shorter. I took out some pieces of each question. They are going to help us classify 2 other kinds of fixed points at the origin. So the first kind we have is a saddle. We've got 2 more. Work through 2 and 3.